Well, after the refraction through prism, now we come towards the total internal reflection. Total internal reflection is a special case of reflection. Normally, the light from the denser medium comes to the rarer medium. When light comes from denser to the rarer medium, it bends away from the normal. We can remember the basic principle. That is, when light moves from rarer to denser medium, the refracted light bends towards the normal. But when light moves from denser to rarer medium, the refracted light moves away from the normal. This fact is to be applied. So in the total internal reflection, suppose we consider a point within the water. The incident light will reach to the boundary of the free surface, it gets refracted. Then, suppose that from the same point we are taking a refraction at another point. We will find that refraction will be at 90 degrees. And in the third case, if we take, we find that light moves in denser medium, it strikes a point on the free boundary and gets reflected in the same medium. Now, this is called total internal reflection. So, this will be now conveyed by a figure and the concept. So, we are coming to the main concept and the figure. So, total internal reflection, the phenomena in case of refraction of light, according to Snell's law, we have mu sine I equal to mu 2 sine R, where I and R represent angle of incidence and angle of refraction. Mu1 is the refractive index of one medium and mu2 is the refractive index of second medium. If light is passing from denser to the rarer medium, as I have explained earlier, if the light is passing from denser to the rarer medium through a plane boundary or the free boundary, then mu1 is equal to mu d, that is refractive index of the denser medium, and mu2 is equal to mu r, that is mu r will be refractive index in the rarer medium. So with mu equal to mu d over mu r, d stands for, that is second medium, or d stands for refractive index of denser medium, and mu r stands for refractive index of rarer medium. Mu d stands for first medium and mu r stands for the second medium. Now, let us clear it from the figure. Now, rarer medium is shown, that is the air medium is obviously the rarer medium, its density is less, and the water medium, that is called a denser medium, its density is more. The density of air as it is expressed in the waves, that is about 0.001293 grams per centimeter cube. And for water medium, the density is nearly 1000 kilograms per meter cube or 1 gram per centimeter cube. Now, according to the figure, we are finding that O is an object in the denser medium. Now, a ray of light is moving in denser medium, that is the incident ray of light, and the point on the boundary where this light reaches, we draw a normal, that is a dotted line. So, when light comes out in the rarer medium, we find that angle I, that is angle between incident and normal, or angle between the incident light and normal is I, and the angle between the normal and the refracted light is R. So we are finding that when light moves from O towards the boundary, it gets refracted away from the normal, as shown in the figure. Now we come towards the second point, point number 2. The normal is again drawn with the dotted line. Now what we are finding that for the same object, if the incident ray is taken at the second normal, the refraction is, that is, along the boundary. And then we consider the third incident ray, that is it is marked with 3. So from object, the incident ray strikes at the free boundary and gets reflected in the same medium. So no light is refracted, but the whole light is reflected in the same medium. Now, this is termed as total internal reflection. It means basically the total internal reflection is a phenomenon in which the incident ray of light from the object gets totally reflected in the same medium. Now we proceed to the next portion, that is sin I, that is equal to mu r over mu d. Here r and d stands for rarer and a denser medium, and mu stands for refractive index. And it is given as mu r over mu d into sin r. Now if we wanted to find sin I, it should be sin I r over mu, because mu r by mu d is taken as mu. So we have two equations, one in terms of sin I and other in terms of sin I and sin r, and in terms of refractive index. Because we know that 1 over mu is sin r over sin I, but mu is equal to sin I over sin r. Now sin I is proportional to sin r with angle I less than angle r, as mu is greater than 1. So angle I, as it was clear from the figure, angle I means the angle between the normal and the incident ray of light in the denser medium, and when it came in the rarer medium, it was moving away from the normal. So obviously angle I must be less than angle R. Now next is, so angle of incident I, that is angle of incidence, or we can say angle of incident, that is I, increases. The angle of refraction R will also increase for a certain value of I, that is less than 90 degrees. R will become 90 degrees. The value of angle of incidence for V is equal to 90 degrees called critical angle, and is denoted by theta C, that is the critical angle. And in the light of equation number 2, that is according to equation number 2, it will be given by sin theta C, that is sine of the critical angle, is equal to sine 90 degrees divided by mu, where mu is the refractive index and sine of the critical angle is 1 over mu. That is the reciprocal of refractive index. So we mark it as equation number 3. Now theta C is the critical angle. As I have explained earlier, that is, if the incident ray of light after striking the rare and denser medium boundary, it gets reflected in the same medium, the phenomena is called the total internal reflection, and angle between the two rays will be known as the critical angle, and that will be represented by theta C. Now, equation 2 in terms of critical angle can be written as sin I is equal to sin R into sin theta C. That is, if I is less than theta C, that is angle of incidence, is less than the critical angle, and sine of angle of refraction is greater than 1, that is greater than sine 90, then this means that R is imaginary, as value of sine of any angle can never be greater than unity, because it is found that sine theta is less than equal to 1, but it cannot be greater than 1. So its limit will be from 0 to 1 only. But if they are tangents and cotangents and secants and cosecants, they will move towards 1 or greater than 1. Physically, this situation implies that refracted ray does not exist, as it is shown in the figure. So the total light incident of the boundary will be reflected back into the same medium, as I have explained earlier from the figure, from the boundary. This phenomenon is called total internal reflection. That is, incident ray in the denser medium gets reflected back into the denser medium after striking the boundary. The total internal reflection to take place, light from air to water or glass and from water to glass, total internal reflection can never take place. When light is passing from denser to the rarer medium, the total internal reflection will take place only if the angle of incidence is greater than a certain value called the critical angle and given by theta c, that is sine inverse 1 over mu, or otherwise we can say sine theta c equal to 1 over mu. So if we wanted to find mu, it should be mu d over mu r, where mu d stands for refractive index of the denser medium, mu r stands for the refractive index of the rarer medium. The third point is rather more important, that is, in case of total internal reflection, that is 100% incident light is reflected back into the same medium. There is no loss of intensity, while in case reflection from mirror or refraction from lens, there is some loss of intensity, as all the light can never be reflected or refracted. There is some loss. This is why the image formed in total internal reflection are much brighter than formed by the mirror or lenses. So this is one of the reasoning part, that in case of mirror and lenses, the brightness of the image is not as clear as in case of total internal reflection.